integrals. I got another question. How did the police get rid of bugs? They call in the SWAT team.
First thing we're going to do is review U-Substitution. That is a technique that allows you to integrate composite functions by substituting U in for the innermost function. So we talked about this in the last lesson. U-Substitution is just where you're given a composite function. Remember, that's just a function within another function. So f of g of x. G is our innermost function, f is our outer function. U-Substitution is where you set u equal to that innermost function. So I let u equal g of x, therefore f of g of x then would equal f of u, because u is equal to g of x. Now let's talk about even and odd functions. So an even function would be a function for which f of negative x is equal to f of x for all x in the domain of f. This means that the graph of f is symmetric with respect to the x-axis. An odd function, however, would be a function for which f of negative x is equal to negative f of x for all x in the domain of f. This means that the graph of f is symmetric with respect to the origin. So let's break this down. An even function would be a function in which, let's say you were to pick some x value, x, and plug it in your function, you would get the y value that corresponds with that, f of x. Then let's say you take the opposite of that x value that you chose, negative x, and you plug that in your function. An even function will give you the exact same y value that you got when you plugged in x. So whether you plug in x or negative x in an even function, you'll end up with the exact same y value. In an odd function, however, let's say you choose that same x value and plug it in your function. You'll get f of x, the y value that corresponds with that. Then you take the opposite of that x value and you plug it in your function. In an odd function, you'll get the opposite y value that you got when you plugged in x. So in an even function, if you plug in opposite x values to your function, you get the exact same y value. In an odd function, if you plug in opposite x values to your function, you get opposite y values. Now, here are the 6 basic trig functions: sine, cosine, tangent, cosecant, secant, and cotangent, and whether they're even or odd. You're going to have to memorize which trig functions are even and which trig functions are odd. And it's pretty easy because only 2 of the trig functions are even, and they're both based on cosine and secant. Now, you may think, how are these even and odd functions? Well, let's look at sine. If I were to plug in some x value, let's say pi over 2 to the function, I get a y value that corresponds with that, 1. Now, let's say I plug in the opposite x value, negative pi over 2 to the function. I get the opposite y value, negative 1. That's why this is an odd function. Cosine would be an even function because if I were to pick some x value, let's say pi over 4, and plug it in the function, I would get rad 2 over 2. If I were to pick the opposite x value, negative pi over 4, and plug that in the function, I would still get rad 2 over 2. Because opposite x values produce the same y value in this function, it would be considered an even function. So again, just memorize which trig functions are even and which trig functions are odd. It's going to come in handy later on. Now let's quickly review the anti-differentiation of a composite function. So this is just saying if you were to take the integral of a composite function that is multiplied by the derivative of that innermost function, what you're going to have to do is you're going to have to use U-Substitution, where you let u equal that innermost function, and then du would be equal to the derivative of that innermost function, dx. And as you can see, this is clearly easier to integrate than this would be up here. Remember, you can just think about this as the reverse chain rule. If I were to take the derivative of this over here, the derivative of capital F of g of x, the antiderivative of f of g of x, I have a function within a function. So I would take the derivative of the outer function, leave the inner function alone, and multiply that by the derivative of the inner function by the chain rule. And I would get f of g of x times g prime of x, which is exactly what this is. So again, we're just using reverse chain rule here. That's what U-Substitution is allowing us to do. Now let's talk about the change of variables for definite integrals. So this says if the function u equals g of x has a continuous derivative on the closed interval from a to b, and f is continuous on the range of g, then the integral from a to b of f of g of x times g prime of x dx is equal to the integral from g of a to g of b of f of u du. So this looks complicated, but it's actually a pretty easy concept. All this is saying is that if you use U-Substitution when evaluating a definite integral, meaning you're given a lower and upper limit of integration, and we set u equal to our innermost function, u is equal to g of x. Then in order to evaluate that integral in terms of u, what you have to do is rewrite your limits of integration. And remember, we're setting u equal to g of x, our innermost function. So all you have to do to find your new lower and upper limits of integration is just plug each of these in for whatever you set u equal to, which in this case would be g of x. That's why each of these are g of a and g of b. Now, one thing I want you to note is that when we use use U-Substitution and rewrite our limits of integration, sometimes the lower limit of integration becomes greater than the upper limit of integration. When this happens, you do not need to switch the limits of integration and put a negative sign out front like we usually do. U-Substitution is the only time you're allowed to have the lower limit of integration be greater than the upper limit of integration, and you'll still get the right answer. Now let's talk about the integration of even and odd functions. So this says let f be integrable on the closed interval from -a to a. If f is an even function, then the integral from -a to a of f of x dx is equal to 2 times the integral from 0 to a of f of x dx. Now this makes a lot of sense because if you think about what an even function looks like, remember if you plug in some x value to an even function and then pick the opposite x value and plug that into an even function, you should get the same exact y value, meaning they're going to be symmetric on either side of the y-axis. So all you have to do is find the integral or area under the curve from 0 to a and then multiply that by 2 because it'll be the same exact area on both sides of the y-axis. Part 2 says if f is an odd function, then the integral from -a to a of f of x dx is equal to 0. And this makes sense if you think about what an odd function looks like. If you plug in some x value to your odd function and then you take the opposite of that x value and plug it into your function, those should each produce opposite y values, meaning that on one side of the y-axis, the area between your odd function and the x-axis will be positive. On the other side of the y-axis, the area between your odd function and the x-axis will be negative, and they'll be the exact same, just with opposite signs. So they'll perfectly cancel each other out. That's why the integral from -a to a of f of x dx of an odd function equals 0.
You ever see an ant farm? Me neither. It's example time.
Now example 1 says evaluate the definite integral. So here we have the integral from 0 to 1 of x times the quantity x squared plus 1 cubed dx. So here we have a function within a function times another function. So this is clearly going to require U-substitution. So we need to figure out what is our u and then what's our du. So what are we going to set u equal to in this case? Well, because we have a function being multiplied to another function, anytime that happens, you want to make sure that you set u equal to whichever function, that if you were to take the derivative of that will include the other function. So I'm going to set u equal to x squared plus 1. The reason is because if I take the derivative of this with respect to x, I get du dx is equal to 2x. Multiply both sides by dx, I get du is equal to 2x dx. And we look at the problem. There is an x and a dx, so that takes care of that. However, there's no 2. So when that happens, you have to take this constant, divide it to the other side of the equation, and you get 1/2 du is equal to x dx, because we can only substitute in for exactly what's there. So now that we have u equal to x squared plus 1 and 1/2 du equal to x dx, we can rewrite our limits of integration. Remember, this is a definite integral this time. And when you're using U-substitution with a definite integral, you must rewrite your limits of integration in terms of u. So how do we do this? Well, we start with our lower limit of integration. In this case, it's x is equal to 0. The way we're going to rewrite it is we're going to take 0 and plug it in for x in whatever we set u equal to. Well, remember, u was equal to x squared plus 1. So we're going to take 0, plug it in for x here, simplify, and we get 1 as our new lower limit of integration. We do the same thing with our upper limit of integration. We're going to take 1, plug it in for x in whatever we set u equal to, simplify, and we get our new upper limit of integration, 2. So now we can rewrite our definite integral in terms of u and du with those new limits. So we're going to take u, plug it in for x squared plus 1. We're going to take 1/2 du, plug it in for x dx. Our new lower limit of integration is going to be 1. Our new upper limit of integration is going to be 2. So now we have our new definite integral that we can evaluate. Well, we need to prepare this for integration. So we take this 1/2, this constant, move it out front of the integral sign, and we're now ready to evaluate this definite integral. So how do we do that? Well, remember, in order to evaluate a definite integral, you got to use the fundamental theorem of calculus. And the first step in doing that is finding the antiderivative of your given function. So what's the antiderivative of u cubed? That's going to be u to the 3 plus 1 power over 3 plus 1. So u to the 4th over 4 plus c. But remember, because we're going to use the fundamental theorem of calculus, we don't need to include plus c because they technically cancel out when we're using the fundamental theorem of calculus. So in order to evaluate this using the fundamental theorem of calculus, we take our upper limit of integration, 2, and plug it in for u. Then subtract when we take our lower limit of integration, 1, and plug it in for u. Then all we have to do is simplify in here and multiply to that 1/2 out front, and we end up getting 15 over 8, which is the exact area under this function on this given interval. Now, really quickly, the biggest mistake made in these types of questions is taking whatever we set u equal to, x squared plus 1, and plugging it back in here for u, and then evaluating it. No! Don't do that. That will give you the wrong answer. We have rewritten our limits of integration in terms of u so that we could more easily use our fundamental theorem of calculus. Just use U substitution, rewrite your limits, and evaluate that way.
I gotta go find food for the queen. You try.
Okay, doing the same thing, except this time we have a function being divided by another function within a function. So this is clearly going to require U substitution. In order to use U substitution, we're going to find our u and du. So what are we going to set u equal to in this case? Well, typically we set u equal to our innermost function. But in this case, we have a function being divided into another function. So we want to make sure that we set u equal to whichever function, that if we take the derivative of that, will include the other function. So I'm going to set u equal to 2x to the fourth plus 1. The reason is because if I take the derivative of this with respect to x, I get du dx is equal to 8x to the third plus 0. Multiply both sides by dx, I get du is equal to 8x cubed dx. Now note, in this problem, we do have an x cubed and a dx, but there is no 8. So anytime you have an extra constant over here, what you need to do is divide that to the other side of this equation, and we get 1/8 du is equal to x cubed dx. Remember, we can only substitute in for exactly what's there. So now, I can substitute this u in for 2x to the fourth plus 1, and I can substitute 1/8 du in for x cubed dx. Perfect, there's no more x's. So now what I can do is rewrite my limits of integration. Because this is a definite integral, and I'm using u substitution, I need to rewrite my limits of integration in terms of u. How do I do that? Well, let's start with our lower limit of integration. X is equal to 0. I'm going to take that 0 and plug it in for x in whatever I set u equal to. So I'm going to take 0, plug it in for x here. I simplify, and I end up getting my new lower limit of integration is 1. Then I'm going to rewrite my upper limit of integration in terms of u. So I take 1, plug it in for x in whatever I set u equal to, and simplify. And I end up getting that my new upper limit of integration is 3. So now that I've rewritten my limits of integration and I have my function in terms of u and du, I can rewrite my integral. So my new integral is going to be the integral from 1 to 3 of, and then I'm taking u, plugging it in here for 2x to the fourth plus 1, taking 1/8 du, plugging it in for x cubed dx. Now all I have to do is just evaluate this integral. So how do I do that? Well, I'm going to make this 1 over u squared, u to the negative second power. I'm then going to take this constant 1/8, move it out front of the integral sign, and now I'm ready to integrate. So remember, when evaluating a definite integral like this, we need to use the fundamental theorem of calculus. And the first step in that is to find our antiderivative in here. So what's the antiderivative of u to the negative second power? That's u to the negative 2 plus 1 power over negative 2 plus 1 plus c. But because I'm using the fundamental theorem of calculus, I don't need to include c because it technically cancels out. Now, if I were to simplify this, I end up getting negative 1 over u, and I can evaluate this using the fundamental theorem of calculus. Then just multiply that 1/8 on at the end. So the fundamental theorem of calculus says I take my upper limit of integration, 3, plug it in for u. Then subtract when I take my lower limit of integration, 1, and plug it in for u. Then I just simplify, multiply the 1/8 on at the end, and I end up getting 2 over 28, which simplifies to 1 over 12. Remember, this is the exact area under the curve of this function on this given interval. Also recall that because I rewrote my limits in terms of u and du, there is no need to plug this back in for u over here. Do not do that, otherwise you'll get the wrong answer. Now example 2 says evaluate the definite integral. So we're doing the same thing. We have a definite integral, and this time we have a function being multiplied by a function within a function. So this is clearly going to require u substitution. The only question is, what are we going to set u equal to? Well, usually you set u equal to whichever function, if you take the derivative of that function, would equal the other function. But that doesn't happen here, because if I set u equal to x minus 1, the derivative of that is just 1, which doesn't take care of this x over here. So this is like the special case that we talked about in the last lesson, where we're going to have to set u equal to the square root of x minus 1. Now the reason I'm going to do that is because normally I would just take the derivative of this with respect to x. Over here, this would get super messy. It would be 1/2 x minus 1 to the negative 1/2 power times the derivative of what's in here. That won't help us substitute in for x and dx. So by setting u equal to the square root of x minus 1, what I can do instead is solve this equation for x, and I can get something in terms of u that I can substitute in for x. So we're going to square both sides here, and we end up getting u squared is equal to x minus 1. We add 1 to both sides, we get x is going to be equal to u squared plus 1. So in this integral, I can plug u in for the square root of x minus 1, and I can plug u squared plus 1 in for the x. The only issue is I still have this dx that I need to plug something in for. Well, what do? Well, here, I can take the derivative of this equation now with respect to x, because I didn't want to do it up here. It had a radical, would have been messy. Down here, though, if I take the derivative of this equation with respect to x, over here, the derivative derivative of u squared is going to be 2u to the first. But since I'm taking the derivative with respect to x, I have to use implicit differentiation and multiply that by du dx. The derivative of 1, well, derivative of constant is just going to be 0. Derivative of x with respect to x is going to be 1. Well, I need to plug something in for dx, which means I need an equation that is equal to dx so I can figure out what I need to plug in for it. So how do I get this equation equal to dx? I just multiply both sides by dx, and I get dx is equal to 2u du. So now I'm able to rewrite this definite integral totally in terms of u and du. I can take u, plug it in for the square root of x minus 1. I can take u squared plus 1, plug it in for the x, and I can take 2u du and plug it in for dx. Perfect. Now, because it's a definite integral, I need to rewrite my limits of integration. So let's start with my lower limit of integration, x equals 5. I'm going to take 5, plug it in for x in whatever I set u equal to, which in this case was the square root of x minus 1. If I plug in 5 for x and I simplify, I end up getting my new lower limit of integration is going to be 2. Now let's do the same thing for the upper limit of integration, 10. So I'm going to take 10, plug it in for x in whatever I set u equal to, simplify, and I end up getting that my new upper limit of integration is going to be 3. So now that I've rewritten my limits, I can go ahead and rewrite my integral in terms of u and du with these new limits. So it's going to be the integral from 2 to 3 of, and then I'm going to take u, substitute it in for the square root of x minus 1. I'm going to take u squared plus 1, plug it in for x, take 2u du, plug that in for dx. Now I have this integral rewritten completely in terms of u and du. So let's go ahead and simplify this, prepare it for integration, integrate, use the fundamental theorem of calculus. So how do I prepare this for integration? Well, I obviously need to simplify what's going on in here. So I'm going to multiply u and 2u, and I get 2u squared. But that 2 is just a constant, which I can move out front of my integral sign. I then can distribute this u squared to the u squared and to the 1. Now I'm ready to find the antiderivative of this function and use the fundamental theorem of calculus to evaluate. So to find the antiderivative of this function, I have to take the integral of each term separately. And I get u to the 4 plus 1 power over 4 plus 1. Over here I get u to the 2 plus 1 power over 2 plus 1 plus c. But since I'm using the fundamental theorem of calculus, I don't need to include c because it technically cancels out. Now what I do in using the fundamental theorem of calculus is I take my upper limit of integration 3, plug it in for each of the u's, then subtract when I take my lower limit of integration 2 and plug it in for each of the u's. I simplify and I end up getting, when I multiply that 2 on at the end, that the area under this function on this given interval is going to be 1,456 over 15 or 97 and 1/15. Again, note, because I rewrote my limits of integration, I did not plug anything back in for u. I just kept it in terms of u and solved it that way.
Did you know there's over 12,000 types of ants? Me neither! You try!
So we're doing the same thing. We have a definite integral, and this time we have a function being divided by a function within a function. So this is clearly going to require U-substitution. So the only question is, what are we going to set u equal to? Well, this is again like one of those special cases where we usually set u equal to whichever function where if we were to take the derivative of it would give us the other function. But if I set u equal to x minus 5, the derivative of that is just 1. That doesn't take care of this x. So what we're going to do is we're going to set u equal to the square root of x minus 5. Now the reason I'm going to do that is because normally I would just take the derivative of this with respect to x. Over here, this would get super messy. It would be 1/2 x minus 5 to the negative 1/2 power times the derivative of what's in here. That won't help us substitute in for x and dx. So by setting u equal to the square root of x minus 5, what I can do instead is solve this equation for x, and I can get something in terms of u that I can substitute in for x. So I'm going to square both sides of the equation. I then get u squared is equal to x minus 5. I then add 5 to both sides of the equation, and I get x is equal to u squared plus 5. So I have taken care of the square root of x minus 5, that's u. I've taken care of the x, which is going to be u squared plus 5. The only thing now I have to find is dx. Well, to find that, I just take the derivative of this with respect to x. So the derivative here with respect to x, derivative of u squared is going to be 2u to the first, but since I'm taking the derivative with respect to x, I have to use implicit differentiation, multiply it by du dx. Over here, derivative of 5 with respect to x is just going to be 0 because it's a constant, and the derivative of x with respect to x is going to be 1. Now again, I'm solving for dx because I need to figure out what I'm going to plug in here. So I multiply both sides of the equation by dx to get dx by itself. I get dx is equal to 2u du. So now I have something that I can plug in for every part of this integral. I can plug in u for the square root of x minus 5. I can plug in u squared plus 5 for the x, and I can plug in 2u du for the dx. Now that I have that, I can rewrite my limits of integration. So we're going to start with the lower limit of integration. I'm going to take 6 and plug it in for x in whatever I set u equal to. So in this case, that would be the square root of x minus 5. If I take 6 and plug it in for x and simplify, I end up getting a new lower limit of integration of 1. Now let's do the same thing for my upper limit of integration, which in this case is 9. I'm going to take that, plug it in for x in whatever I set u equal to, simplify, and I end up getting that my new upper limit of integration is going to be 2. Now that I've rewritten my limits of integration and I can rewrite this definite integral in terms of u and du, we're going to do that. So this is going to become the integral from 1 to 2 of, and we said we're plugging in u for the square root of x minus 5, we're plugging in u squared plus 5 for the x, and we're going to plug in 2u du for the dx. Now all we have to do is just simplify this in here, and we can evaluate it using the fundamental theorem of calculus. So how do we simplify this? Well, the 2 is just a constant, which I can move out front. The u's here cancel each other out, and I'm just left with 2 times the integral from 1 to 2 of u squared plus 5 du. Now what I can do is evaluate this using the fundamental theorem of calculus. My first step is to find the antiderivative of the function in here. So what's the antiderivative of u squared plus 5? Well, I'm going to integrate each term separately. The integral of u squared is going to be u to the 2 plus 1 power over 2 plus 1 plus c. The integral of 5 is going to be 5u plus c. The c's combine to make one constant of integration, but because I'm using the fundamental theorem of calculus, I don't need to write plus c because it technically cancels out. Now let's evaluate this using the fundamental theorem of calculus. I'm going to take my upper limit of integration, 2, and plug it in for each of the u's. I'm going to subtract when I plug in my lower limit of integration, 1, for each of the u's. I then simplify, and I end up getting the exact area under this function on this given interval is 44 over 3. Notice that I did not plug the square root of x minus 5 back in for u. We don't do that when we rewrite our limits of integration. Now example 3 says find the definite integral. Here we have the integral from negative pi to pi of sine cubed x dx. So before you do anything here, you should look at your lower and upper limit of integration. And that should tip you off that something's different here. We're going from negative pi to pi. They are opposite x values. What that means is that this function is likely either going to be an even or odd function. If it is an even or an odd function, we can integrate it fairly easily using the theorem that we talked about before. If it's not, we can always go back and use some other technique to integrate this. So let's check, is this an even or an odd function? How do we determine that? Well, we're going to choose some x value to plug into this function that will give us a non-zero y value. So what's an x value I can plug in for sine that will give us a non-zero y value? How about pi over 2? I'm going to plug in pi over 2 here, and if I were to evaluate this, sine cubed of pi over 2 is the same thing as sine of pi over 2 cubed, which is 1 cubed, which is 1. So we got a non-zero y value. Perfect. Now what I'm going to do is I'm going to take the opposite of that x value. I'm going to take negative pi over 2 and plug it into this function. If I get the exact same y value, if I get 1 again, I know that this is an even function. If I get negative 1, then I know it's an odd function. If I get neither of those things, then it's neither an even or an odd function, and I have to go back and integrate some other way. So let's simplify. Sine cubed of negative pi over 2 is the same thing as sine of negative pi over 2 cubed, which is negative 1 cubed, and negative 1 cubed is negative 1. So I have opposite y values here, meaning if I were to plug in opposite x values, I get out opposite y values, meaning this is going to be an odd function. And if you have access to a graphing calculator, you can always graph this to confirm, and you see, yes, in fact, we do have an odd function, where if you were to plug some x value into your function and look at the y value that corresponds with that, and then plug in the opposite of that x value to the function and look at the y value that corresponds with that, those y values should be opposite y values, and they are. What that means is we look at our theorem, which says if I'm taking the integral from negative a to a of some odd function, it's going to be equal to 0. So the integral from negative pi to pi of sine cubed x dx, this odd function, has to equal 0. That would be the total area under this function on this given interval. And it makes sense because all of the positive area will perfectly cancel out with all of the negative area on that given interval right there.
Did you know queen ants could live for several years and have millions of babies? Me neither. You try.
We again have a definite integral where the lower and upper limit of integration are opposite x values. That should tip you off that this is likely going to be either an even or an odd function. So we have to determine which is it. To do that, we're going to choose some x value to plug into this function that gives us a non-zero y value. So how about pi? If I were to plug in pi for x in this function, cosine of pi is going to give you negative 1. Now what I'm going to do is take the opposite of that x value and plug it in the function for x. So I'm going to take negative pi and plug it in the function function for x. So what is cosine of negative pi? It's still -1. Meaning, if I plug in opposite x values to this function, I get the exact same y value. When that occurs, that means your function is going to be an even function. And if you have access to a graphing calculator or graphing utility, you can confirm that with your graphing calculator. You can see that if you were to plug in some x value to your function and look at the y value that corresponds with that, and then plug in the opposite of that x value to your function and look at the y value that corresponds with that, those y values should be equal to each other. Perfect. Now we look at our theorem. How do we evaluate even functions? What I'm going to do is I'm going to rewrite this definite integral. Instead of the integral from -pi/2 to pi/2 of cosine of x dx, it's going to be 2 times the integral from 0 to pi/2 of cosine of x dx. These two things are equivalent based on the theorem we talked about previously. Now all I have to do is evaluate this definite integral on this interval. So how do I do that? Well, to evaluate this definite integral, I need to use the fundamental theorem of calculus. First step in that is finding the antiderivative of our given function. What's the antiderivative of cosine of x? That would be sine of x plus c. But because I'm using the fundamental theorem of calculus, I don't need to include c because they cancel out during the fundamental theorem of calculus. Now I use the fundamental theorem of calculus and I plug in my upper limit of integration for x and subtract when I plug in my lower limit of integration for x. I simplify and end up getting 2 times 1, which is 2. That would be the area under this function on this given interval.